Alright, good afternoon. So today we are going to finish acceleration analysis. Tomorrow will be the exam. And next week we are going to start force analysis. So I extended the due date for the homework to the next Monday. So tomorrow, Friday, is not going to be the due date for the homework. So you can turn it by Monday in class. So we started driving the acceleration analysis, acceleration equation for absolute slided crank. So we talked about the constant, variables, nouns and unknowns. So in displacement analysis, the unknowns were theta 3 and d. In velocity analysis, it's going to be omega 3 or theta dot 3 and d dot. And in acceleration, it's going to be theta double dot and d double dot. So we differentiated the velocity equation So these are two velocity equations that we derived on velocity analysis. If we differentiate them, we are going to get the acceleration. Again, I'm going to repeat how we can differentiate. A is constant, derivative of angular velocity is going to be angular acceleration. Derivative of this times this, negative A, theta double dot 2, sine of theta 2, negative A theta dot 2, derivative of this with respect to time, theta dot 2 cosine of theta 2. Right hand side, derivative of d dot, it's going to be d double dot. B is constant, I should differentiate theta dot 3, it's going to be negative theta double dot. Now I should differentiate this multiplied by these two. This is the first equation. Second equation is going to be A, derivative of this, theta double dot 2 cosine of theta 2, minus, let me write, A theta dot 2, derivative of this with respect to time is going to be negative theta dot 2 sine of theta 2. Right hand side B is constant, I should apply derivative for this. A minus or B theta dot 3, negative theta dot 3 sine of theta 3. So the unknowns are theta double dot 3 and d dot. So these two terms. These terms has theta double dot and theta double dot 3. And here this term has theta double dot, there is no d double dot. The other terms are noun. This is noun, this theta double dot 2 is given, theta 2 is given. So the other terms are not. I'm going to keep the unknown term in one side, I'm going to move this guy to the other side. So I'm going to get d double dot minus b theta double dot 3 sine of theta 3 equals to this this one theta dot theta 2 dot times theta 2 dot is going to be theta 2 dot square negative 8 theta dot 2 square cosine of theta 2. If I move this to the left side, it's going to be positive, and this multiplied by this is going to be a square. Cosine of theta 2. And second equation, this is the only term that I have as unknown. Theta b theta double dot 3 cosine of theta 3 equals to this. This is the negative 8 theta 2 dot square sine of theta 2. And if I move this to the other side, it's going to be positive. Yes?
I'm having trouble figuring out where the theta dot 2 squared.
Theta dot 2 squared. This one?
Yeah.
When I differentiate that term, I've got this one. Negative 8 theta dot 2 times parenthesis theta dot 2 cosine of theta 2. So this times this.
Oh, distribution.
Yes. The reason that I put in parentheses because this is the derivative of this term, sine of theta 2. If I want to differentiate this with respect to time, it's going to be derivative of sine of theta 2 with respect to theta 2 times derivative of theta 2 with respect to time. Chain rule. So this is theta dot 2. This is going to be cosine of theta 2. Any other question? So let me, in velocity and acceleration analysis, we are going to form the equation in this way. Unknown in one side, known terms in the other side. We want to do that to write the equation in the system of matrix form. So now I'm gonna write these two equations in the matrix form. The unknowns are d double dot and theta double dot 3. D double dot and theta double dot 3. Angular acceleration of link 3 and acceleration of the slider. Here I'm gonna have 2 by 2 matrix, and the right side I'm gonna have the constant part. Constant part would be this side, negative a theta double dot 2 sine of theta 2 negative a theta dot 2 square cosine of theta 2 plus b theta dot 3 square cosine of theta 2. This is for the first equation. For the first equation, the coefficient of d double dot is 1. So this cell is going to get 1. This guy is going to get the coefficient of theta double dot 3, which is negative b sine of theta 3. So I'm done with the first equation. Second equation, the constant part is coming here, a theta double dot 2 cosine of theta 2 minus a theta dot 2 square sine of theta 2 plus this guy, this term is gonna get the coefficient of d double dot. This second equation doesn't have d double dot, so the coefficient is 0. 0 times d double dot is gonna be 0. The coefficient of theta dot double dot 3 is positive d cosine of theta 3. So this is the matrix form of acceleration equation. You need to use the matrix form to solve this system of equation by MATLAB or your calculator. In exam, you have access to your calculator, so you should plug in the coefficient matrix and constant matrix and solve for d double dot and theta double dot. Good. So now let me compare the the acceleration equation with velocity equation. So when we derive the velocity, when we did the velocity analysis for this, we wrote the vector loop equation, displacement equation. We differentiate those two equations with respect to time. We derive them, and we could end up to this matrix form. Matrix A times matrix X, the variable were d dot and theta dot 3, and right hand side is matrix B, which is a constant. If you compare this matrix with this one, they are identical. 1 minus b sine of theta 3, 0 b cosine of theta 3. So when you are going to do the acceleration analysis, you don't need to recalculate the matrix A. You already done this on velocity analysis. The only thing that you need to calculate is constant part, which is matrix B. Here we have different terms. In velocity equation we have different vectors. So the coefficient matrix is going to be the same in velocity and acceleration. If you have any question about this, it's like that. Otherwise, I'm going to go and solve one example on using chemical. And it's obvious that we should do the analysis for each mode. So if we do, first we should do displacement. You might end up with two modes. Two modes, one mode, or 0 possible modes. If you get two modes, you do the velocity analysis for each mode. And then we are gonna do the acceleration analysis for each mode. So you run this system of equation twice. So let's work on this example just. We are given with the offset slider crank with the length of 3 inch, B is 8, and the offset is 2. We would like to do velocity acceleration analysis when theta 2 is at negative 30, and omega 2 or theta dot 2 is 15 radian per second clockwise. When I say clockwise, meaning that omega 2 should be considered negative. Clockwise is negative, counterclockwise is positive. And the angular acceleration of link 2 at this angle is theta double dot 2 is 10 radian per second squared. Look at the units. The angular velocity is radian per second, the angular acceleration is radian per second squared. It's clockwise, meaning that alpha 2 or theta double dot 2 is negative 10 radian per second squared. We should do the displacement analysis. First mode, we get D equals to 9.79 and theta 3 for the first node is 205.94. First node. And for the first node, the velocity analysis is going to give us d dot equals to negative 41.42 unit per second. I assume it's inch, or you can consider different units. Inch per second. Theta dot 3 is going to be 5.42. So for the second node, we can get D and theta 3, but I'm going to do this only for the first node. So matrix A is going to be 1 minus B is 8. B is 8. Sine of 45.9. 0 is cosine of 45. Matrix B is longer than matrix A. It has 1, 2, 3 pairs. Make sure that you plug in the numbers with the correct sign. And matrix B is going to be negative A is 3, negative 3 times theta double dot. Theta double dot is 10 clockwise. I said it should be negative, so negative 10. It's a common mistake that I have seen the student make before. They forgot about the sign. It's a clockwise, it should be negative. Times sine of theta 2. Theta 2 is negative 30. Second term is negative A, negative 3 times theta dot square. It's 15 clockwise, meaning theta dot 2 is negative 15 radian per second. So negative 15 square is going to be same as positive 15 square, but you plug in negative 15 to be consistent. Cosine of negative 30, and last term is B cosine of 205.9 times omega 3 squared. Omega 3 is positive 5.4. And matrix B, the second row is going to be negative positive 3. Theta double dot, which is negative 10. Cosine of negative 30. Negative 3 times negative 15 squared, sine of negative 30 plus 8 sine of 205.9 5.4 squared. If we do the math, A matrix is going to be 1, 3.94, 0, negative 7.196, and matrix B or vector B you do math for these three, the summation of these three terms, you end up to negative 645.9 or 94.5. So in MATLAB you use A backslash E and hit the enter, you will get the results which are you will get negative 374.8 and negative 68.71. The first one is for the first variable, which is d double dot. So the acceleration of the slider is going to be negative 374.8. If the unit is inch, it's going to be inch per second square. If it's meter, meter per second square or centimeter. And theta double dot is radian per second square. Radian per second square. It's negative. The acceleration would be in clockwise direction. If I ask you about that. Let me check. Matrix A is negative 8 times sine of degree 205.9 0 8 times cosine of let me enter the numbers. sine of negative 30 times negative 10 squared minus 3 times cosine degree of negative 30 multiplied by negative 15 squared. Last term is 8 times cosine degree times 5.4 second row 3 times cosine degree of negative 30 multiplied by negative 10 squared negative 3 times sine of times negative 15 squared.
For the beginning of the ball, what do you put at negative 10?
I made mistake.
So negative 3 times negative 10. All the way to 3.
Second row. This guy? Oh, it doesn't have power. Thank you. Even for the first. I can do it. 8 times sine of degree of last term is 205.9 multiplied by 5.4.
Make sure you do it to the top. You need to pick up the square on the top. Make sense? The top.
I cannot divide it. Let me go with this, then I can. 809, 209. Is it the same as? So it's very similar to this A backslash B. This is the correct answer. 707.6. It's close to what we got on the slide. Since I didn't enter the angles with decimal, so we are gonna get close number to negative 709 and negative 39. We make which is going to be negative 810, 197, and 208.8. So this is how you can do acceleration analysis for offset slider crash. Alright, any question on this? So let's do the same step for 4-bar mechanism. In 4-bar mechanism, in displacement analysis, theta 2 was given. We were solving for theta 3 and theta 4. In velocity, theta dot 2 is given, we are solving for omega 3 and omega 4. In acceleration analysis, we first perform displacement and velocity analysis, and then when theta double dot 2 is given, we are solving for angular acceleration of link 3 and link 4, which are theta double dot 3 and theta double dot 4. Everything is going to start from vector loop equation. As you see, this vector plus this vector equals to this plus this. We get the displacement equation in x and y. We differentiate that to get the velocity equation, which is these two equations. And if we differentiate with respect to time, I'm not showing the steps, I'm just jumping to the final equation. We will end up to these two equations. So if I rearrange the equation, I'll end up to this matrix form. So matrix A times matrix X, which is theta double dot 3, theta double dot 4, should be equal to matrix B, which is here. If I show you the velocity equation, this is forward mechanism. We derive the velocity equation in the matrix form by ending up to this system equation. Matrix A is identical to matrix A that we derive for acceleration. Same as after the slider crank. Once we got matrix A, you don't need to calculate it for acceleration. The only thing that you need to calculate again is matrix B, which is the line matrix. Good? So now let's do one class activity. We are done with displacement, velocity, and acceleration analysis for the mechanism. Now, I'm looking for acceleration of point B. What would be the acceleration of point B? Or any other point in this mechanism? Point B is one point that I picked. What should we do to find acceleration of point B? And if you remember, I told you why we are interested about finding the acceleration of any point, because I cannot build mass of this by the acceleration of center of gravity, then I know how much force is going to apply to that vehicle. Then I can do design based on the force applied to that specific. So, any tau.
So you get the vector from O2 to B, and then you find like a fast vector.
That's true. First, you connect origin to point B, you will get the vector OB, and try to reach point B through the different paths, either going through this path or this path. I'll go through this path. So vector OB is gonna be O2B. Is gonna be O2, O4 plus O4B. X component of this O2B is gonna be X component of point B. This vector X component of that is gonna represent the X component of point B. Right hand side, O2, O4. D cosine of 0 plus C cosine of theta 4. And Y component of O2B is going to be Y coordinates of point B. This sine of 0 plus this sine of theta 4. If I simplify this, cosine of 0 is 1, B plus C cosine of theta 4. And for this is going to be C sine of theta 4. If you are looking for velocity, you differentiate once. D is not changing, so D dot is going to be 0. C is not changing, it's going to be coefficient. Derivative of this with respect to time, negative C theta dot 4 sine of theta 4. Do this for velocity in Y direction. C is constant, I just differentiate theta 4 with respect to time, C theta dot 4 cosine of theta 4. Now, if you are looking for acceleration of point B in X direction, differentiate this with respect to time one more time. C is constant, derivative of this is going to be C, negative C theta dot 4 sine of theta 4, negative C times this, derivative of this. Derivative of this is going to be cosine theta dot 4 cosine of theta 4. And we are done with X component. For Y component, C is constant, I should differentiate the first term. Second term, this is theta double dot times cosine of theta 4. I'll keep this. Derivative of this guy is going to be negative theta dot 4 sine of theta 4. C is now given. Theta double dot 4 is coming from acceleration analysis. Theta 4 is coming from displacement analysis. It's coming from velocity analysis, and these two coming from velocity and displacement. So you have X component and Y component of point acceleration of point B. Question on this. So I can ask you, suppose we have a terminal links instead of binary links on the tree. I can ask you find the acceleration of this point or any other point. Again, what you need to do, you need to reach to this point by adding the vector, either moving from this path or this path. So if we go from this path, the X component of point P, we have done this before for velocity analysis. The X component of point P is going to be A cosine of theta 2 plus RAP, which is, or RPA, this one, times the angle of theta 2 cosine of angle of theta 2 plus delta 2. This is constant, it's given, so we are writing theta 2 plus delta 2. Y component just change cosine to sine. If you differentiate once, you will get velocity equations. If you differentiate twice, you will get acceleration of point P. So for example, if you want to know how much force is going to apply to this, find the center of gravity, the location of that. Write the coordinates of this point by adding the vectors, and then differentiate twice. You will end up with something like this. Find the acceleration of center of gravity, acceleration of center of gravity for link 3 in x direction. Find the value. Find the acceleration of center of gravity for link 3 in y direction. If you multiply this by mass of link 3, you can find the force which can be applied to link 3 in y direction and x direction. And this is what we are going to do in force analysis of a mechanism. Question on this. When we go to the force analysis, it's gonna be, we are gonna use whatever we covered so far for displacement, velocity, and acceleration analysis of the mechanism to find the force and the torque applied to any mechanical mechanism. We are gonna cover it in 1 or 1.5 weeks, and then we are gonna finish the mechanism analysis. We go to the mechanism synthesis or design of the mechanism. All right. Tomorrow, the step lab has celebration for tomorrow, starting at 8:30 to 10:30. That would be great if you can stop by to see how it's gonna look like after renovation. We have the exam. We are gonna start at 2:10. The exam will be on Science Center Hall.
So if we attend the celebration,
I just announced.